Hello learner, today we will study about the asymptotic notation. I am Ajay Kumar, Assistant Professor, Department of Computer Science and Informatics, Central University of Himachal Pradesh. So we will study asymptotic notation in details, that is your block 1 unit 2. So first we have to study about what is asymptotic notation. The main idea of asymptotic analysis is to measure the efficiency of algorithm that do not depend upon the machine specific constants and do not require algorithm to be implemented and time taken by programs to be compared. Okay, so asymptotic notations are mathematical tool to represent the time complexity of algorithm for asymptotic analysis. Actually, asymptotic terms come for the time and space analysis of any of the solution of the any algorithm. So here we can compare the time complexity and space complexity. So how to solve what are the notations available in that is growth of the functions, you can say. So these are the notations: theta notation, big O notations, omega notation, small o notation, small omega notations. So these 5 kind of notation we generally use to the growth of the functions. When n increases, then the theta notation have a different value, the big O notation have a different things. So theta notation that gives the average case, big O notation gives the big O notation is like worst case analysis, omega notation is best case analysis, and the stricter version of best case and worst case is like in worst case we can use a small O notation, and in best case a small omega notation in a strict version. Okay, so we will first moving towards the notation. First we have to know the basic concept about the bounds. What is the meaning of bound? So there are 2 kind of bound, that is the lower bound and upper bound. So lower bound is a non-empty set A and its subset set B is given with the relation less than equal to an element A belongs to A is called the lower bound of A if A is less than equal to X for all X belongs to B. So for we can see through the example. For example, a non-empty set A and its subset B, that is A equal to 1, 2, 3, 4, 5, 6 and B equal to 2, 3, the lower bound of B equal to 1, 2 as 1 and 2 belongs to set A. Okay. So upper bound means an element A belongs to A is called upper bound. B if X is less than equal to A for all X belongs to B. For example, if A equal to 1, 2, 3, 4, 5, 6 and B equal to 2, 3, the upper bound of B is, that is 3, 4, 5, 6, as 3, 4, 5 is in set A and is greater than equal to the all elements of B. Okay. So the a bound or upper bound or lower bound is said to be tight bound if the inequality is like asymptotic bound less than or equal to. If we use the less than equal to, that bound is known as the tight bound. Similarly, a bound, lower bound or upper bound is said to be loose bound if the inequality is strictly less than. Okay. So in pictorial representation of tight and loose bound, that is less than equal to. So distance between lines in first figure you can see distance between lines A and B is less than equal to A for large value of X. Actually X value is increased, will approach A as it is less than or equal to A. But in case of like loose bound, here you can see A less than B, there will be a distance between A and B even for a large value of X as it is strictly less than only, because in figure first it may the value of X will be increased, A will be A will moving towards B, but in case of A less than B, that is loose bound, A and B is moving far away for moving for greater value of X, or can say the greater value or larger value of input side. So this is the tight bound and this is the loose bound. Again, one important concept is bounded above and bounded below. What is the meaning of bounded above and bounded below? So in respect of function defined on non-empty set X, bounded above is written as fx is less than equal to A for all X belongs to X. Then we say function is bounded above by A because the above boundary is capital A of fx. It is read as function for all elements in the set X is less than equal to A. Similarly, bounded below is written that A, that is capital A function, is less than equal to fx for all X belongs to capital X, it is said to be function is bounded below by A. It is read as function of for all the elements in the set X is greater than or equal to A. A function is said to be bounded if it has both bounds, that is bounded above and below both. It is written as fx is greater than or equal to A and lesser than or equal to B for all x belongs to X. You can see through the pictorial representation. So here bounded above means the boundary value of fx is A. You can compare with like big O also. So for in case of big O, fx have a boundary value c times gx, and bounded below you can see in fx equal to c times gx in bounded below. And in case of like both bounds, in case you can see the theta notation, in theta notation fx have a two boundary, that is c1 times gx and c2 times gx. Okay, so bounded above means you can see the you can see like bounded above means the worst case complexity, bounded below means best case complexity, and bounded both bounded means that is average case complexity. So coming to the theta notation, this is after the value of bounding, that is theta notation will be used, that is it provides both upper and lower bounds for a given function. Like in last example, both bounds will be available for fx a and b. So in theta notation, theta of gn equal to fn, there exists constant c1 and c2 and n naught such that fn is greater than c1 times gn and less than equal to c2 times gn for all n greater than n naught. So in this example also, so the above expression can be described as fn is theta of gn, then the value of fn is always between c1 times gn and c2 times gn for large value of n, obviously n greater than n naught. The definition of theta also requires that fn must be non-negative, because you can see in definition fn is greater than c1 times gn and this c1 times gn is also greater than equal to 0. So this all about talking about the non-negative values for value of n greater than n naught. So this is the graphical representation. Here you can see fn, and fn have a both boundary, lower boundary and upper boundary, that is c1 times gn and c2 times gn. So fn equal to theta times gn you can say. So theta notation includes the function from above and below. Since it represents the upper and lower bound of the running time of an algorithm, it is used for analyzing the average case complexity of an algorithm. So the execution time is a lower and upper bound on the algorithm's time complexity. It exists as most and least boundary for a given input values. So theta provides the exact bound. Okay, exact means average bound, that is upper and lower bound. So I am taking one example to show 3n plus 1 equal to theta n. So after comparing with the mathematical definition theta theta times gn equal to fn, so you have to calculate the c1, c2 and n naught. So in this case, what will be the value of fn and gn? So in the given problem, fn equal to 3n plus 3 and gn equal to n, because here fn equal to theta times gn. So fn equal to 3n plus 3 and gn equal to n. So to prove fn equal to theta times gn, we have to calculate the c1, c2 and n naught such that fn must be greater than equal to c1 times gn and lesser than equal to c2 times gn for all n greater than n naught. So to verify, first this problem will be broken into two parts. First fn is less than equal to c2 times gn. So fn equal to 3n plus 3, that is less than equal to gn. Gn means that is your n. So I have used 3n, okay, because 3n plus 3 is always less than equal to 3n plus 3. So for fn in terms of gn such that mathematical inequality hold, here I have used the 3n extra term. So 3n plus 3, that is 6n. So overall you can see 3n plus 3 must be greater than 3n plus 3 must be less than equal to 3n plus 3, that is 6n, and in this case we can get c2 equal to 6 for all n greater than n naught value equal to 1. If we put the value of n naught, that is 1, so and the left hand side, that is 3n plus 3, that is 6, and in right hand side 6n means n value equal to n naught value equal to 1, that is 6, and after the value of n naught, that is 1, greater than 1, that is if we put the 2, then 6 into 2, that is 12, and 3 into 2 plus 3, that is 9. So overall, after this n naught value and C2 value, you can see Fn must be less than equal to 3n, Fn must be equal to C2 times Gn. And the next part is, first half we can get the C2 and n naught, and in second part you have to verify Fn must be greater than C1 times Gn, that is also greater than equal to 0. So here Fn equal to 3n plus 3, and that is greater than equal to Gn equal to 3n. So here 3n plus 3 is always greater than equal to 3n. Why? Because if we use the 3n plus 3, that is plus 3 terms is extra, and here we use C1 equal to 3 and n naught equal to 1 for every value of C1 and n naught, that is C1 equal to 3 and n naught equal to, after n greater than n naught, that is n greater than 1, this inequality holds, 3n plus 3 greater than equal to 3n. So in second part, C1 equal to 3 and n naught equal to 1, and in first part C2 equal to 6 and n naught equal to 1. So finally we can see this inequality will hold when C1 equal to 3 and C2 equal to 6 and n naught equal to 1. So that is after the value n naught equal to 1, we can get the this notation will be hold, that is 3n equal to theta n. Next is BIGO notation. Similarly, you can prove like n square plus 1 is equal to theta of n square. Many problem like quadratic, like anything you can solve through this approach. First, divide the problem into two half. First you verify Fn is less than equal to C2 times Gn, then verify Fn is greater than C1 times Gn, and correspondingly you can get the value of C1, C2 and n naught, and you can get the theta notations value. Next is BIGO notation. So BIGO notation represent the upper bound of running time of an algorithm, therefore it gives the worst case complexity of an algorithm. So BIGO of Gn equal to Fn, there exists positive constant C and n naught such that Fn must be less than equal to C times Gn. Obviously it will be greater than 0 for all n greater than n naught. So if Fn describes the running time of an algorithm, Fn is BIGO of Gn. So if there exists a positive constant C and n naught, so Fn must be less than equal to C times Gn for all n greater than n naught. So it returns the given input highest possible output value. Highest possible output value means it is the worst case. So this is the graphical representation, that is after n naught, n greater than n naught, we can see the Fn have a upper boundary, that is C times Gn. So I have taken some example of BIGO notation, like if I say 3n square plus 4n plus c 6 equal to BIGO of n square. So in this case Fn equal to 3n square plus 4n plus 6 and Gn equal to n square. For solving this, you have to check the inequality. The equality is 3n square plus 4n plus 6 is less than equal to n square. So because here the Gn is n square, so comparing the Fn highest power, that is n square, here also n square, and the coefficient of Fn is 3, n square coefficient is 3, so we use the 3n square, and the rest of the less power, that is 4n plus 6, for 4n plus 6 we have used n square. So 3n square plus n square, that is 4n square. So after the c value, that is 4 and n naught equal to 6, how to calculate n naught? Because if we put the value of n naught equal to 1, 2, 3, 4, 5, and after 6 you can see the Gn, C times Gn is must be greater than Fn. So we can identify C equal to 4 and n naught equal to 6. So in this case, this Fn 3n square plus 4n plus 6 equal to BIGO of n square. So this value C and n naught, it's not an unique value, it may be other value also depending upon your C and n naught. C and n naught have different pairs also for holding this inequality. So one of the pair is C and n naught is C equal to 4 and n naught equal to 6. Next is omega notation. Omega notation represents the lower bound of the running time of an algorithm. Thus it provides the best case complexity of an algorithm. It is defined as the condition that allows an algorithm to complete statement execution in the shortest amount of time. That is, shortest amount of time means that is best case complexity. That will give the minimum time. So omega of Gn equal to Fn, there exists C and n naught. So Fn must be greater than or equal to c times gn. Obviously, it will be greater than 0 for all n greater than n naught. So, let g and f be function from set of natural number to itself, and the function f is said to be omega of g if there exists a constancy. The same definition will be written here in a simpler form. So, this is the graphical representation of omega notation. So, Fn have a lower bound, that is lower bound c times gn, and after n greater than n naught, that will Fn must be greater than c1 into gn. So, I have taken one example, n2n square plus 4n plus c 6 and omega n square. So, Fn is 2n square plus 4n plus 6 and gn equal to n square. If we check the inequality, that is 2n square plus 4n plus 6 is greater than n square. So, just comparing the coefficient, we make 2n square, and after getting the value of c equal to 2 and n naught greater than 0, any value greater than 0, if we take 0 value, then left hand side will be 0 and right hand side will be 6, that is obviously greater than or equal to 6. So, in this case, one of the pair c and n naught equal to c equal to 2 and n naught equal to 0. For this pair, this inequality hold, Fn equal to omega of n square. So, next is a small o notation. Actually, we already studied about the big O notation. Big O notation means that is the worst case time complexity. So, a small o notation, that is strictly, that is not greater than equal to, so it is only greater than. So, for a function that does not asymptotically tight upper bound, okay, so a small o notation is used. It is used to denote an upper bound that is not asymptotically tight, that is loose bound. So, let a given function gn, and big O of gn is the set of the function fn defined as big O of gn equal to fn for any positive constant c, there exists n naught must be greater than or equal to 0, such that c times, here you can see the inequality. Here inequality is 0, fn must be greater than 0 and less than, not less than equal to. If less than equal to is there, that is the big O notation. So, this is loose bound. Okay. So, after n greater than n naught, we can see c times gn, fn have a upper boundary, but this boundary will be loose bound. Okay. So, you can see this example through big O of a small o notation, fn equal to 2n plus 4 and gn equal to n square, to show fn is less than c times gn. So, fn equal to 2n plus 4 and gn equal to n square. So, at every case n square is greater than 2n plus 4. So, c must be greater than 0 obviously, and n not equal to 1 for every value of c. Like c, if we take c equal to 1 and n not equal to 1, we can see that 2n plus 4, n square is always greater than 2n plus 4. So, for the value c equal to 1 and n not equal to 1, this inequality will be hold, 2n plus 4 equal to a small o n square. So, we can calculate that the lower degree polynomial have a higher degree polynomial small o notations. If we use the lower degree polynomial equal to a small o notation of higher degree polynomial, that must inequality will be hold. A small omega notation, that is also the part of omega notation, it is also a loosely bound, and for a function that does not have asymptotic tight lower bound, that is omega notation is used, and it is used to denote a lower bound that is not asymptotically tight, that is loose bound. Let a given function gn and omega of gn is the set of function fn defined. Omega of gn equal to fn for any positive constant c must be greater than 0. There exists a constant n not greater than 0, such that here you can see fn greater than, not greater than equal to. If greater than equal to will be there, then omega notation will be there. So, fn greater than c times gn, and it is obviously greater than 0 for all n greater than n naught. So, in this figure, function fn is loosely bound below the constant c times gn. Okay, and in the small o notation, here you can see the pictorial notation, c times gn is upper bound, and here c times gn is lower bound, but this is loosely bound, and in case of omega notation, this will be the tight bound. So, this is the example. Again, the reverse the example of a small o notation and a small omega notation. Here, the higher degree polynomial equal to a small omega notation of lower degree polynomial. You can easily satisfy Here you can see the Fn equal to 2n square plus 4n plus 6 and Gn equal to n. So, Fn greater than Gn only hold the Cn into 2n square plus 4n plus 6. If C value equal to 1, 2, 3, any value, but when we put the C value equal to 1 and n not equal to 1, you can see if we put the value of n equal to 0 also. So, what will be the value? Left side equal to 0 and right side equal to 6. So, higher degree polynomial is always greater than lower degree polynomial. So, here you can see Fn equal to omega of Gn, that is this inequality hold, and it is reverse of a small o notation. Okay. So, this is the pictorial representation of asymptotic notations. If we compare all the notations like Fn, big O notation, you can see just the upper bound, that is the that you can see the tight bound. A small o notation, that is loosely bound. Okay, and this hold only greater than. Here is big O notation hold greater than equal to. You can see the omega notation and the small omega notation. Small omega notation will be the loose bound and the omega notation is the tight bound. So, you can see the value of n and the effort of this asymptotic notation inclination. So, if comparative analysis of asymptotic notation, what will the value? If I say Fn equal to big O of Gn, that means you can see above all the above pictorial representation. Say this analogy hold less than equal to. If Fn equal to a small o of Gn, that hold only less than, and Fn equal to big O of Gn, that means Fn must be greater than. Okay, and what will be the reverse of this? You can see Gn equal to big O of Fn. Okay, if I say Fn equal to a small omega of Gn, that means you can see Gn equal to a small o of Fn. So, this inequality hold for greater than, and if I say Fn equal to theta times Gn. So, if we break the Gn, the two things will be there, that is Fn equal to big O of Gn and Gn equal to big O of Fn, because you can see the definition of theta. So, theta of Gn, what we write? We write C1 times Gn is less than equal to Fn and it must be less than equal to C2 times Gn. So, this Fn equal to theta times Gn will be the combination of both the things. So, this is the analogy of all the notation, big O, small o, omega, small omega and theta notation. So, what are the general asymptotic notation properties? What is the property of asymptotic notation? First is, if Fn is big O of Gn, then A into Fn is also the big O of Gn. A is any constant. If we multiply something, you can get the same, like 2n square plus 5 is if the big O of n square you can write. So, 7 times Fn, when we multiply any constant, the big O value cannot be changed. Similarly, this property satisfies with the theta and omega also, right? We can say if Fn is theta times Gn, then A into Fn is also the theta of Gn, where A is any constant. And again for omega also, if Fn is omega of Gn, then if we multiply any constant, then A into Fn is also the omega of Gn, where A is any constant. So, this property hold for both theta and omega also. This property is known as the transitive property. So, transitive property means if Fn is big O of Gn and Gn is big O of Hn, then Fn is big O of Hn. So, if this is the example, Fn equal to n, Gn equal to n square and Hn is nq. So, increasing power, polynomial power. So, you can see n is big O of n square and n square is big O of nq, then n is big O of nq. Obviously, it will be true. But similarly, this property satisfies theta and omega notation also. Okay. So, Fn equal to theta of Gn and Gn equal to theta of Hn, then Fn equal to theta of Hn. Obviously, for omega also, Fn equal to omega of Gn and Gn equal to omega of Hn, then you can directly say Fn equal to omega of Hn. Reflexive property. The reflexive property is always easy to understand. Fn is given, then Fn is big O of Fn, since the maximum value of Fn will be Fn itself, like x equal to Fn and y equal to big O of Fn. So, if the example Fn equal to n square is big O of n square, or you can see big O of Fn. Similarly, this property satisfied the theta and omega also. If Fn is given, then Fn is theta of Fn, and Fn is given, then Fn equal to omega of Fn also. Symmetric property, if Fn equal to, Fn is theta of Gn and Gn equal to theta of Fn, okay, Fn is theta of Gn, then we can say Gn is the theta of Fn. If I say Fn equal to n square and Gn equal to n square, then the property will be hold, Fn equal to theta of n square and Gn equal to theta of n square. So this property only holds for the theta notation, symmetric property. Transitive symmetric property, if Fn equal to big O of Gn and Gn equal to big omega of Fn, then Fn equal to n square, example Gn equal to n square. So we can say n is big O of n square and n square is omega of n. So this property only holds for omega and big O, big omega and big O. So some more properties, like if I say Fn equal to big O of Gn and Fn equal to omega of Gn, then we can say Fn equal to theta. We already discussed in previous slides. If Fn equal to big O of Gn and Dn equal to big O of En, then Fn plus Dn equal to big O of max Gn and Dn. Example, you can say Fn equal to n, Dn equal to n square. If you add Fn and Dn, that is n square, and that is also the big O of n square. In this example, if Fn equal to big O of Gn and Dn equal to big O of En, then Fn into Dn, and in above example Fn plus Dn. So in both the cases, big O holds. Okay. So this is all about the all kinds of asymptotic notations and the examples related to asymptotic notation. So we have to careful about the all 5 notation. Basically we have 3 notation only: big O notation and the small o notation, big omega notation and small omega notation, and the theta notation. So you have to take care all the properties and the basic differences between big O and small o, big omega and small omega. So thank you so much.